Bonjour, geometry friends. Time for doing some more circle proofs. But before we get into the proofs, we're going to start off with a little old school circle stuff. So let's do a little review. Look at the diagram, and I want you to figure out the coordinates for the center point of the given circle and the length of the radius for the given circle. And once you have those values determined, please write the equation of the circle that's in that diagram. You probably won't take too long to do this, so I'll talk for a couple seconds while you're figuring out your center point is at 5, 5, and that your radius is 3. And then once you have that information, you know that you can put it into the standard form for the equation of a circle. So your equation ends up as x minus 5 squared plus y minus 5 squared equals 9. Now, let's consider the equation of the circle x squared plus y squared equals 1. What is the center and radius of that circle? Hopefully you wrote down that the center is at 0, 0, and your radius is at 1. So now we're going to look at the transformation that would move the circle with a radius of 1 centered at 0, 0 to the location of the circle that's in your picture. So any standard basic circle centered at the origin, radius of 1, looks something like that. What transformations would be performed on that circle to create the original given circle? So what would happen? How would it move? Which direction? And how would we change the equation? Well, our radius goes from a radius of 1 with the circle that's centered at the origin to a radius of 3 with the given circle that's drawn on our page already. So what we have to do is adjust our equation. The center point itself goes from the origin 0, 0 to the center point of 5. So the transformation that occurred was a translation of 5, 5 to the right 5 and up 5. So that's a translation of 5, 5. And we did a dilation scale factor of 3. Now you can do the dilation first and the translation second, but if you're going to have the dilation centered at the origin, it's easiest to do the dilation. But it's easiest to do the dilation centered at the origin. You could do it at a different point, but it's easiest to do it when it's centered at the origin. Okay, so then it asks, is this a similarity transformation or is it a congruence transformation? So is it a rigid motion or is it a similarity transformation? And the answer is a similarity transformation. The objects are similar because they are not the original, they are not the same size. And any transformation that involves a dilation is a similarity transformation because the shapes are similar, not exactly congruent. Nice little old school review. All right, now we are here today to do proofs. So on with the proofs, please. Here we go. Example 1, given arc AR is congruent to arc AM. That's what those symbols are supposed to be above the AR. It's supposed to be an arc and an arc. It's not always easy to get notation software that makes good arcs when we're trying to type up our diagrams and questions. But given that arc AR is congruent to arc AM, prove that triangle RAM is isosceles. Every proof starts out with the givens. Okay, so arc AR is congruent to arc AM. Sorry for my congruent sign being a little out of whack there. Again, it's not always easy getting things to format correctly. That should be there. And I will color that out while you're filling it in. You might even be able to do the proof. This is only a 3-step proof. Are you done yet? Do you know? Do you know enough rules? Do you know enough rules to finish this off? Well, if arc AR is congruent to arc AM, that means segment AR is congruent to segment AM because congruent arcs intercept congruent chords. And if those two chords are congruent, that means two sides of our triangle are congruent, and I told you 3 steps. Triangle ARM is isosceles. If a triangle has 2 congruent sides, It is isosceles. So pause if you need to. If I'm going too fast, I doubt I'm going too fast for this one, and me talking right now might be enough for you to get the rest of that proof written down, and then you can turn your page. So turn the page. We have a fill in the blank proof coming up next. Next on our docket is a fill in the blank proof. So here we go. AB is a diameter of circle O. AD is congruent to FB. I should mark that on my diagram. AD is congruent to FB. There we go. CD is perpendicular to AB, and EF is also perpendicular to AB. Did you know that if two lines are perpendicular to the same line, then that means they are parallel to each other? Did you know that? You might not have known that. We're not going to use it here, but that's something that we could use if we needed it. Two lines that are parallel to the same line, I'm sorry, two lines that are perpendicular to the same line would be parallel to each other. All right, so I just accidentally erased my congruence marks, so let me throw those back on. You got your given written in, and off we go. OC is congruent to OE. Well, look at the diagram. OC and OE, why are they congruent? Well, they're both the radius of the same circle, so all radii of the same circle are congruent. And it is imperative that you write of the same circle. It does have to be there, because I've had students in the past write the statement, all radii are congruent. Think about that. Is every radius of every circle ever created the same as every other radius? No. Not all radii are congruent. All radii of the same circle are congruent. So be careful with that. So why don't we go ahead and mark those? And if you look at the next set of statements, same thing. OA is congruent to OB. Those are still radii of the same circle. So we can mark those congruent. That's OA and OB, which are technically also equal to CO and EO. We could have done all four of those in the same line, but whoever wrote this proof decided that it would be nicer to separate them. Next, piece OD plus piece AD equals the full segment of OA. When you take the two parts of a segment and add them together to equal the full segment, do you remember what that is? Yes, that is correct. I couldn't quite tell who said it, but I heard someone say it. Segment addition postulate. That means the parts add up to equal the whole. The parts of the smaller segments added together equal the length of the whole big segment. Now looking at step 4 and then comparing it to step 5, what moved and what changed? What moved and what changed? Well, hopefully you noticed that the plus AD turned into a minus AD on the other side of the equal sign. And same goes with the FB and the FB. So that just means we subtracted on both sides of the equal sign. Subtraction property of equality. Okay, you got that written down? Good. Now we have OD equals OB minus OF. That's just substitution. So the substitution is coming from the givens, where AD is congruent to FB. So then AD turns into FB. And then since OA is congruent to OB, then the OA turns into the OB. All right. There we go. So there's substitution. Now I have OD equals OB minus FB. And right above it, I have OF equals OB minus FB. So then by another substitution or transitive property, we get OD congruent to OF. So you can mark that on your diagram. Now you might be able to finish the proof from here. Out of the given information, why is CDO a right angle and why is EFO a right angle? Why are they right angles? You may have already have it written down and I'm just wasting your time. Hopefully not. Perpendicular lines form right angles. That is totally true. And if they're both perpendicular lines, I'm sorry, if they're both right angles, then all right angles are congruent, so we can say they're congruent to each other. But that leads us, if we look at your diagram and what you have labeled carefully, that leads us to angle, side, side, and we cannot use angle, side, side. So I've said this several times, if you end up with a situation where you are using right angles and get angle, side, side as the reason why your triangles are congruent, you cannot use angle, side, side, but it tells you that what we need is to turn our triangles into right triangles, and then the right triangles we will be able to use hypotenuse leg. Then we can match up our corresponding parts. And then we got some circle reasoning to use. I should add HL congruence. There we go. So we turn our triangles into right triangles because a triangle with a right angle is a right triangle. And our triangles are congruent by hypotenuse leg. Then we can match up COA and angle EOB because they are CPCTCs, corresponding parts of congruent triangles are congruent. And then we're trying to prove that arc AC is congruent to arc EB. So we're trying to prove that arc AC is congruent to arc EB. And we just said that the angle COA is congruent to angle EOB. So in our previous statement, we said that this central angle is equal to this central angle. And the central angles are congruent to the intercepted arcs, which means angle COA is equal or the same as arc CA. Angle EOB is equal to arc EB, and we don't have to prove that because we actually already did a proof in our notes, but we have the fact, the rule, the theorem, the end result, the last line of our proof. Congruent central angles intercept congruent arcs. Turn the page. Okay. Turn the page. This one we are doing from scratch. We are trying to prove that given that QS is a diameter and QR is perpendicular to PT, we're trying to prove PQ times QT is equal to QS times QR. All right, so look at that diagram. There are a ton of different triangles inside that circle. We have to sort through our given information and figure out which triangles we are actually trying to prove congruent. So let's do that. All right, QT. I'm sorry, that's PQ. PQ is over here. So that has to be the side length of one of my triangles. And then QT has to be aside from the other triangle. It can't be the same triangle because the parts are being multiplied together. So that means QT is from a different triangle. That's why I used a different color to highlight it. Now QS. QS could be part of the yellow triangle or it could be part of the blue triangle. But if you look at the diagram, QS, segment QS, does not make a triangle in any way with side QP. So that means I'm going to do the QS is blue. And then which means to make those two blue segments into a triangle, TS would be the third side. All right, so then what about the yellow one? The next or last segment we have mentioned here is QR. If I look at QR, all right, I need to make a yellow triangle out of those two yellow pieces, so that's PR. So that kind of gives me the idea of which triangles we're going to prove, or I'm sorry, which triangles we're going to use. As far as what to prove, we're supposed to prove that PQ times QT is equal to QS times QR. Do you remember how to prove that segments are equal? Well, when we did this back in unit, I don't remember. I think it was unit 6. What we did is we took this and made it into a proportion. So it'll be PQ, QT have to be diagonal because they get cross multiplied, and then QS and QR are the other two. So we're going to have a reason why we can create that proportion, and then we'll do cross product property to get to the end of our proof. Now, this, back in our similarities unit, came from angle-angle similarity. So that means with that in mind, we need to get two pairs of congruent angles so that we can then set up the proportion, because corresponding sides of similar triangles are proportional, CSSTP. And then we could then do the cross product property and finish our proof. Okay, so we need two equal angles. Now, off to the proof. All right, so first things first, givens. And then we need some equal angles. Well, we got a pair of perpendicular lines there, so I know I'm going to get a right angle somewhere. The right angle in the yellow triangle, angle QRP, will be a right angle because perpendicular lines form right angles. Let's look at the blue triangle. How am I going to get a right angle in that blue triangle? Well, what I'm going to focus my attention on is the fact that this inscribed angle is half the measure of the intercepted arc, and the intercepted arc happens to be the endpoints of a diameter. And there is a rule, a law, a theorem for that. Thales' theorem. Thales' theorem says an inscribed angle that intercepts a diameter is a right angle. Mathematically, the inscribed angle here is half the intercepted arc, so it's half of 180, so it's 90 degrees, so it's a right angle. All of that can be summarized in Thales' theorem. Easy rule to write. All right, so there's one of our right angles. Why don't we go ahead and take care of the other right angle? Perpendicular lines form right angles. And then once I have two right angles, I can either make them congruent or maybe I'll have to use HL. HL is if we're trying to prove two things congruent. So we are trying to prove these two triangles similar. So we want our angles congruent to each other. All right angles are congruent. Next, we need to figure out a pair of angles that intercept. Somehow we need another pair of equal angles. See anything? I do. Let me show you. Guess let's go with a nice burgundy. Okay. So I have either angle R, well, no, that one's the right angle. So I have either angle Q up here that I can try to deal with, or I can have angle P. So here's what I'm going to do. I'm going to take the vertex of angle P, trace both sides of angle P to where the other end of that segment hits the circle. Because that angle at angle P is an inscribed angle. So let's figure out the arc that it is half the measure of. So that inscribed angle is half the measure of arc QT. QT. Oh, it's such a QT. That inscribed angle is half of that pink arc. Now, it just so happens that our other inscribed angle from the other triangle over here intersects the circle at the same 2 points. So this angle here intercepts the same arc. So we had a rule for that. There's a rule for that, just like there's an app for that, only this is a rule. There's a theorem, actually. Sorry, there's a theorem for that. Inscribed angles that intercept the same arc are congruent. And there we go. Bam, bam. Two sets of equal angles. You should be able to finish the rest of this proof. So I'm going to do it super quick, and then you can pause if you need to fill it in. And we've done that 100 times this year. Angle-angle similarity, CSSTP, when you set up the proportion, and then cross-product property with the proportion to your final proof statement. All right. Simon says, let's do one more. So let's do one more. Here we got a bunch of given chords, a circle, AC congruent to BD. Those are segments, AC congruent to segment BD. Good to know. I guess I should go ahead and mock it. It mocks itself because it's a smart mock. Okay, so that's really all we got. One pair of equal, oh, sorry, one pair of equal segments. Let's move those. There we go. We got one pair of equal segments and we have a circle, and the rest of it's up to us to figure out. Well, if you look at the two triangles we are trying to prove congruent, let's see if there's anything significant between those two triangles that we can use. I want a lighter blue. All right, right there. Here and there. So we got reflexive property. Let's nail that down so it's secure and in our proof. CB is congruent to CB by the reflexive property. So that gives us two sides already, two pairs of congruent sides. Now we need something else. Oh, well, how about this? Angle CAB and angle CDB both have endpoints at C and B. So those are inscribed angles that intercept the same arc. So inscribed angles that intercept the same arc are congruent. That's one wonderful tastic. Now, but again, that leads me to angle side side, and I don't have any right angles to turn it into HL. And angle side side does not work, so that means I got to keep going. I have some information, but I don't have enough to say the triangles are congruent yet. So why did they give us AC and BD? I know why. There's a rule that we talked about. Congruent chords intercept congruent arcs. So if chord AC is congruent to chord BD, that means arc AC is congruent to arc BD. And that becomes significant because even with all this stuff done in here, if arc CA is congruent to arc BD, then the angles, inscribed angles opposite those arcs, and inscribed angles that intercept equal arcs, congruent arcs are congruent. Now that is a different rule from rule number 5, because the first rule said inscribed angles that intercept the same arc are congruent. This one says inscribed angles that intersect congruent arcs are congruent. Now with all that done, I don't know if you can tell, but with those angles congruent to each other, that one there, and that one there. Now we have angle similarity, or angle side, which technically I gotta needs to be angle side congruence. Okay, there is 4 example proofs done super well, and super good luck to you working through the problem set. Some fill in the blanks. There are some calculations to do, and there are answer keys on Teams to help you through with whatever you need. So I'll talk to you soon. Best luck, good wishes, stay healthy, and goodbye.